class. Today we're looking at warm-ups 1.6, and we'll be dealing with transformations of parent functions. This warm-up is what we had put on last day's lesson, trying to use the graphing calculator. We will hopefully spend some time in class taking a look at this. So let's just examine a little bit of it right now. So looking at example A, we know our parent function is a quadratic because it's y equals x squared. Okay? And what we need to notice is that, ladies and gentlemen, is that looking at the different colors, we know that our parent function is in the black. Okay? And when we look at what the key point is when x equals 1, in this case, y equals 1. So 1, 1 is our parent key point. What happens to that point when we look at the red line, so the red graph? Instead of it being 1, 1, it's 1, 3. So what's actually happened is it's been stretched vertically by 3. So in this case, we're going to write down A equals 3. Just give me 1 second. I've got to pause. Sorry about that, guys. I just had to realign my graphing, my screen here. So again, we were looking at the key point for f at x in the black, and we noticed that the key point in this case was 1 and 1. Okay? When we look at the key point when it's y equals 3x squared, we know that it's 1 and 3. So what does that tell us? That the y component has been stretched by 3. So what does that tell us? A equals 3. Likewise, when we look at the green expression, when x equals 1, y equals 1/2. So what does that tell us? Instead of being stretched vertically, it's been compressed. So A in this case equals 1/2. Okay, because it's half the way between 0 and 1 on the y. And lastly, let's take a look at the blue one. Instead of it being 1 and 1, it's been flipped. So instead of being -1 and 1 and -1, it's now 1 and -2. So it's been stretched. So in this case, A equals -2. The negative tells us that it reflects the x-axis, and 2 means it's vertically been stretched by a factor of 2. Let's take a look at the second one, ladies and gentlemen. Okay? Key point, again, is going to be what's happening to y when x equals 1. So we look at our parent function, which is in the black. We notice that we've got the ordered pair 1, 1. That is true for all parent functions, ladies and gentlemen, that ordered pair 1, 1. Okay, so 1, 1. When we look at the red, ladies and gentlemen, instead of 1, 1, it's now 1 and 3. So again, that means that it's been stretched 3 times, so A equals 3. Looking at the green, ladies and gentlemen, it's half of what it used to be. So instead of actually being stretched vertically, it's being compressed. So A equals 1/2. So it's a vertical compression. It's being squashed. Okay? And again, when we take a look at G equals -2 times the square root of x, again, it's negative, so the negative part tells us it reflects the x-axis, and the 2 part means that it's in a vertical stretch of 2. You will find that as a similar pattern when you take a look at the reciprocal in C. Again, key point here was 1, 1. Okay? What happened to it between the black graph to the red graph? It became the point 1, 3. Okay? What happened in the green graph? It became the point 1 and 1/2. And likewise, for our point for A, we notice A equals -2, so it became 1 and -2. All right? So that happens in each case. Let's quickly take a look at the D, the absolute value. Okay? Again, the same thing. When x is 1, y is 1. When you look at the red one, when x is 1, y is 3. And for the next one, x is 1, y is 1/2. All right? So that again was the review. If you hadn't had a chance in class, we're going to take a look at the graphic calculators, pull them out so you can see that. Let's take a look at today's lesson, ladies and gentlemen. Today's lesson is 1.6, transformations of parent functions. One thing to note, ladies and gentlemen, that because P and Q deals with majority of just a vertex, we're changing those letters to D and C, simply because not all of our parent functions have a vertex, so we use it D and C, and that's used for transformations, i.e. the D tells us the left-right movement, and the C tells us the up and down movement. I'm just going to pause for a second. All right, class, sorry, I'm back with that. So what we're going to do, ladies and gentlemen, is take a look at any parent function. So we're going to start here with y equals f at x. And then we're going to apply the a to it. And the a in this case is any ordered, the a is any value that's out front of the entire function. So again, you're going to apply the a. What does that mean? That means you're either going to have a vertical stretch or compression, and it will reflect the x-axis if negative. So first of all, we take a parent function. We're then going to apply the a to it. After that, we're then going to take a look, hey, what's the horizontal translation? So what we're going to say here is that the D, apologize, cut right off there, the D is going to tell you the left-right movement or horizontal translation. So that's going to be left or right movement. And then finally, we're going to deal with what we call the vertical translation, which is C, and that is your up or down movement. Okay? What we will have, ladies and gentlemen, is a general formula, which is in this box here. You're going to want to write that down. And this general formula is what we have is all the transformations that can be applied to any function. Please note this formula looks different because there's an f at x inside or on the right side that tells us we can't graph this as it is. Basically, it says, hey, we can take a value of A, a value of D, and a value of C and apply it to any parent transformation. Okay? Sorry, something just glitched with my computer. Hopefully we're back. Okay? So let's take a look at that and apply it to some parent functions. So first of all, we take a look at a parent function. In this case, we're going to go y equals x squared, which is our quadratic. So we start with that. We're going to apply a to it. And then we're going to say a subtract d, which means it's squared because that's within the parent function itself. And then we're going to just add c to the end. Again, you're using this formula from above, but we're just specifying, hey, we're going to apply those to the actual quadratic formation. Sorry, quadratic function. Okay? Next example. Let's apply the a, d, and c to the square root function. Okay? So again, the parent function is the square root function here. So that we start with the parent function, we add the a in front of it. Then remember that the x minus d. Okay? And then at the end, you add the c. Looking at the next one, ladies and gentlemen, this is the reciprocal function. Again, this is a trickier one, simply because when you add a, it actually goes on the top as a numerator, because a times 1 over x equals a over x. And then again, the d goes right beside the x, so it's going to be x minus d. And then we take a look at finishing it off, you add c. Last one we'll take a look here is the absolute value. So the absolute value, just treat it as the brackets, ladies and gentlemen. It is a special type of brackets. So the a goes out front. Then we subtract the d inside the absolute values, and then you add the c at the end. So basically, let's just scoot back up here, folks. What it's saying is this equation here, we can apply to any parent function, and we can substitute in any transformations for all three of those. You can't graph this expression as it is because it's not related to any parent function. Once we tell you the parent function either being quadratic or square root or reciprocal, or absolute value, then we can graph it once we've done our proper substitutions. So let's take a look at an example here and how we're going to do this. Okay? So looking, ladies and gentlemen, at our g at x here, okay, notice g at x equals -3 times any function, subtract 2 plus 3. This does not specify the parent function, so you cannot graph it as is. But what we can do is say which transformations can be applied to any parent function. So all we're going to do is relate this to that equation we wrote above, or I can just rewrite it down here. So g at x equals a times f times the function subtract d plus c. So from this, we know some information. We know, for example, that a equals -3. What does the negative tell us? Negative tells us it reflects the x-axis, and the 3 tells us it's a vertical stretch by a factor of 3. The D part, ladies and gentlemen, tells us that it's a horizontal translation, i.e. we go right to. Whereas C, ladies and gentlemen, C is 1 that tells us we're translating up 1. And again, we could perform these transformations or translations to any of our parent functions. So now what it says to write that above transformations, and now we're going to specify which parent function we're going to use. So for A, ladies and gentlemen, we're going to transform it to a quadratic. So basically you sub in your A, your D, and your C into the quadratic form. Now, this you can actually graph because the function notation is taken out of the right side. Okay? Likewise, take a look at the second one. We're taking it and saying the parent function is the square root. So again, we're going to apply the A, the D, and the C. It's substituted.
Any staff member that has set their deviation sheet down, please do so now.
Okay? And then the last two, this parent function is the reciprocal. So again, we're going to take a look. A is -3, so it goes on top here, ladies and gentlemen, and then it's divided by x minus d, which is -2, and then you add 1. Then you can graph that. Again, once you've got the parent function, you can graph these. Okay? Unlike up top here, you couldn't graph it up here because you didn't know what your starting point was, i.e. which function to start with. Looking at our last one here, it's the absolute value. And again, you sub in the A out front, x minus d, and plus c. Any questions with that? Please come and see me in class. Let's go to our next page. Let's try example 2. For each function, state the parent function and the transformations required. So in example A, you should notice that in the expression you've got x squared. That tells you your parent function is quadratic and your parent function is f at x equals x squared. The other things you should notice, ladies and gentlemen, is that the A equals 3. That tells you you have a vertical stretch by a factor of 3. And C is +2, which means you have a vertical translation up 2. Okay? Let's take a look at example B. Hopefully you recognize the x's on bottom, ladies and gentlemen. So hopefully you recognize this as a reciprocal parent function. Okay? And then based on that, the A is -2. The negative part tells you it reflects the x-axis. And the value of 2 tells us it's a vertical stretch by a factor of 2. D, ladies and gentlemen, be careful here. D, although it looks like it's got x plus 1, remember it's x minus d. So how does the negative become a positive? It has to be a negative value. So in this case, you're going to notice that, I apologize, I erased that. For the D value, guys, if you see a positive sign in your equation, it's the opposite, which means it is a negative. So D equals -1. That's a horizontal translation, 1 left, or left 1. Okay? Whereas C equals -3, that's an easy one. It's out at the end. That's your vertical translation. It tells you you're going down 3. Negative tells you down. 3 tells you how many. All right, let's try one more here, folks. C. Hopefully you can recognize the absolute value signs. Okay, that tells you your parent function is the absolute value. A is out front, okay? A is 1/2. Okay, what does that tell us? Because A is less than 1, instead of being a vertical stretch, it is a vertical compression. So we're actually flattening it from the above and below. Okay, so vertical compression by a factor of 1/2. Okay, looking at D, D equals 5, which is a horizontal translation, right 5, and C equals 3, which is a vertical translation, up 3. Okay, so ladies and gentlemen, your homework today is a handout that I've provided. Please give that a try and try to do as many as you can, okay? And again, come see me in class if you need any help. Have a good day.